So everyone, good, not really morning, but not afternoon yet. So in the middle of it, and welcome to our online seminar series on the space science and technology. And today's distinguished speaker is Professor Mike Gruntman, professor at the Department of Astronautical Engineering, University of Southern California. And Mike and I are old friends, so to say. We met each other when we were young, much younger than we are today. And I think that moment, I don't remember whether I met you in Moscow or when you're already, outside Moscow. But anyway, Mike, he did his graduate study in space physics at the famous institute, Space Research Institute in Moscow. We call it IKI, and he spent 15 years there, right? You spent 15 years, yeah.
Correct. From a 19-year-old student for 15 years.
And he learned everything he needs to learn. the masters there. I mean, so you may hear him later talk about the great master like Gringos, and people like that. He moved to America and became a faculty at the department, I think, aerospace engineering. Am I correct? Yeah.
Yes, that's correct.
At the aerospace engineering of USC. I think the time was 1990. And later on, as far as I can tell, he's kind of single-handedly created this Department of Astronautical Engineering all by himself. And he started a program, the Master of Science, but in Astronautical Engineering program, which is very popular at USC. And I think many aerospace engineers learn their trades by coming to this class, to Mike's class. And he's going to tell us what this program is about. I think that there's something that we can learn from him, from USC, and then we hope that from that somehow we can have some cooperation in the future. Mike, please go ahead.
Thank you very much, Wing, for your kind introduction. I'm grateful to have this opportunity to talk to our colleagues in Taiwan. And so I will be talking about our program, Master of Science in Astronautical Engineering. So on the left, there's an agenda of this talk. I will start very briefly, general about space engineering education in the United States, then about the university and the School of Engineering, then about the department, and after that, concentrate on the program Master of Science in Astronautical Engineering, because now everything will be in the perspective by that time. I will talk about some statistics about distance education that is very important, and about bolts and nuts of our degree, requirements, coursework, and the student groups. And I will conclude with the lessons learned. On the right, there is listed 4 key publications about the program, and they can be downloaded, combined as a one file from astronauticsnow.com/aste.pdf. And I will send a PDF of this talk, of the slides, to Betty, and if somebody is interested, please contact her, and this file will be available with the references of the URL and all that. All right, space or aerospace education in the United States. In the country, at first, aeronautical engineering departments were formed beginning from the 1930s, supporting the growth of the aviation industry. On the right, there is a graph showing how many programs or departments were activated among the universities through the decades, starting from 1930s until today. And you will see that there was obviously surge in the 1930s and 40s and 50s, driven by aviation, but the growth continued even from 2011 to 2020, 9 new departments were formed. And today in the United States, more than 70 ABET accredited Bachelor of Science degrees, and ABET, it's accreditation board that accredits all undergraduate engineering programs, educational programs. Graduate programs, masters and PhDs are not accredited usually. So we have more than 70 in the country Bachelor of Science programs and more than 50 Master of Science programs in aerospace. So what happened as these are aeronautical engineering departments, and when the space age began in the 1950s, these departments became home for space engineering education. And most of the department, overwhelming majority, changed their names around 1960 to either aerospace or some combination of aeronautics and astronautics. In around year 2000, we at USC called for establishing separate academic departments in astronautical engineering, and we succeeded to do that. And we remain the only full-scale program in the United States in astronautical engineering. Other universities still continue to be aerospace and astronautics and aeronautics. Now, the rationale for establishing separate departments was that traditional aerospace departments remained focused on aeronautical part. That means fluid mechanics, structures, and all that, primarily aeronautical for the supporting aircraft industry. And space was sort of a second-class citizen there. And we argued that to having all kinds of departments, aeronautical engineering, aerospace, and astronautical, would create competition, and this will lead to the balanced mix of the offered programs determined by the needs of the aerospace enterprise. So now about the university. We are a big university, the oldest private university in the Western United States, founded in 1880, more than 40,000 students, half graduate, half undergraduate. Students are coming from all states of the Union, from 100 countries. And our School of Engineering is rather highly ranked nationally. It has 8 academic departments, including astronautical engineering. Again, this is a unique department in the United States. And we research universities. Our School of Engineering has about $200 million research grants and contracts, a lot of students, 2,700 undergrads, and more than 5,000 graduate students. The department. So we started to build a specialization in space engineering within the aerospace engineering department in the 1990s when I joined the school. And by 2004, the master's program grew dramatically. It created some actually tensions within the department, focused on aeronautical science, as practically all departments in the United States. And in 2004, our forceful dean, and with the support of the university president, established a new special department of astronautical engineering, 100% focused on space, pure space engineering. And as I said, we are the only department in the country that offers full set of astronautical engineering degrees, Bachelor of Science, Master of Science, Engineer, PhD, and a certificate. Certificate is basically a mini master's program. If, for example, to get a master's degree, one needs 10 classes, certificate usually 4 or 5 classes focused on some narrow area. And on the master's level, we are among the largest in the country and probably one of the big also in the world. Now about our faculty. We are a small department within the school, small in terms of full-time faculty. We have only 4 professors, only we all are full professors, 4 tenured professors. Actually, we are getting the 5th one in August as an assistant professor, young fellow joining us. We also have 1 professor of practice. A professor of practice means it's teaching position, and no research is expected, just only teaching classes, and 1 research faculty, research professor. And we are supported by a full-scale staff support. We have 6 people supporting us, and this is because we have a very large student population, so many staff members. Although we are very small in terms of full-time faculty, we have 24 part-time lecturers, and we are taking advantage of our geographical location in Los Angeles, which is Southern California is still a center of the space industry. A lot of space enterprise and space companies are there. And these full-time working professionals, they are top specialists in their fields, and they teach part-time in our program, and they teach primarily specialized graduate courses in our master's program. For undergrads, you need really instructors on campus, some interaction needed with the graduate master's program, part-time lecturers, and some of them online. It works very well. And these part-time lecturers are coming from all these top companies that are surround Los Angeles. It's Boeing, Northrop Grumman, the Aerospace Corporation, Aerojet Rocketdyne, NASA JPL, and others. We're a research university. So, and our school itself, engineering school, characterizes as a research university in terms of volume of research and numbers of PhDs that we produce. So we are a full-time faculty. We are doing science, and on the right, you see some areas where we're working: astronautics, space environment, space physics, propulsion, space mission design, and others. At the bottom left, there's a photo of a 24 of books that are published by our faculty and the adjunct faculty part-time lecturers. So we're really nothing special. We're a typical research university, which does research, teaching, publishes articles, books, and so on and so forth. We also have some student projects, rocket propulsion lab and liquid propulsion lab, and I will talk a little bit more about that because it's important for our educational program. A little bit statistics. So we're relatively young, 20 years old, but we already graduated 300 roughly Bachelor of Science degrees and more than 1,000. Actually, by today, it's 1,050 Master of Science degrees. It's a very big number. And close to 60 PhDs. On the right, there is a dynamics of the number of degrees that we offer every award every year since 2004. So during the last 4 or 5 years, we're giving roughly 75 or 80 degrees per year, masters of students. And if you look at the figure on the right, it has different colors, light orange and blue. Blue is full-time students on campus. They study full-time. And this light orange on top is a fraction of online students who work full-time and study part-time. A little bit more about this in a few minutes. So about 1/2 of our graduates to whom we give the degrees, they are online students, and 1/2 on campus. On the top left is the dynamics of the number of master's degree in aerospace awarded in the United States nationally. So it was about 600 around 2000, and today it's 1,600. Now, the national statistics compiled by the American Society for Engineering Education does not distinguish between space, aeronautics, and astronautics. It's put everything together in a big aerospace group. So total today, roughly 1,600 in the United States being awarded. As I mentioned, there are more than 50 Master of Science programs in the United States. So on average, Each program should be about 2% of the national. And the bottom left, there is a figure showing fraction of our pure space program as a fraction of the national number of the master degrees. And we are, during the last 5, 7, 10 years, we're between 3 and 5%. So our program, Master of Science program, is a factor of 2 larger than the average program in aerospace in the United States. So if you think about this, space engineering is a smaller part of aerospace. Aeronautical sciences dominate aerospace because simply aircraft industry is much, much bigger in terms of financially than space. And a little bit more about this later. So we are among the large programs nationally, twice as large as the aerospace program nationally, but we are pure space. If there were statistics in pure space engineering that we don't have, my guess is that we probably would have accounted for 15–20% of the national Master of Science degrees in space engineering. But again, this statistics doesn't exist. The degree is in a highly dynamic area, and the program designed for those who have Bachelor of Science degrees in science and engineering and who want to work in the space sector or in the space defense sector, deal with the building spacecraft, rockets, and operate them. As I mentioned, distance education, half of our students online, and they are served through the distance education network. In a minute, more about that. On the right, there is a slide showing the reach of our online program. And you can see that in the United States, we cover practically every state where there is a space industry or space-related industry or government centers. We have students from there. We also have students from Canada, from some exotic locations abroad where American military are deployed. Some officers are enrolled in our program. And in Canada, in international, it's always a possibility for international students to enroll. We do not require Bachelor of Science degree in aerospace, just Bachelor of Science degree in science and engineering, any area. I will talk a little bit more about that. This is very important because this is reflects the composition of the space industry. And we have small astronautics full-time faculty on campus, focuses on fundamental classes, and practically all specialized courses are taught by part-time lecturers from industry, Boeing, Lockheed Martin, Northrop Grumman, Aerospace, and others. Online. Let me just say a little bit. So my school, School of Engineering at USC, was very active in distance education since 1970. And obviously the technology has been evolving. In 1970s and 80s, the classes were televised by television channels to the companies surrounding Los Angeles area. Then we started to beam our classes to customers through the transponders on geostationary satellites. And today, it's obviously the internet. Anybody with a high-speed connection can get classes, very high quality of the delivery of classes. One half of our master's degree is awarded to students who work full-time and study part-time. Let me just explain this a little bit. Big companies, large legacy companies such as Boeing, Northrop Grumman, Raytheon, and others, they hire Bachelor of Science, graduating Bachelor of Science. And then they tell them, by the way, you can pursue part-time Master of Science in any area of engineering, part-time, basically taking one course per semester, you still work full-time, and we, the big company, we will pay your tuition, and tuition are pretty expensive. So this is a major incentive for engineers to take courses online, and this became online education became the way of life in the United States, in the space industry, defense industry, aerospace industry. And many students in these big companies, government centers such as NASA, the Air Force, and others, they take classes and work on their Master of Science degrees through distance education at different universities. There's a few dozens of the leading engineering schools that offer such programs. We also see now the increase in students from small companies, small space companies that start supporting. There are also students who support themselves without any support. They're paying for their tuition, also online, and active duty military. Some military officers who see that they will retire from the armed forces in, say, 5-8 years. They start preparing what they will be doing when they become civilian, and getting an advanced degree in space engineering would open for them a door to the space industry. Now, the requirements to the online students are identical to those on campus. It's indistinguishable, the same admission criteria, the same coursework, the same lectures, the same homework, the same exams. And the students can get Master of Science degree without stepping on campus at all, completely online. And the quality is exactly the same. And as I said, 1/2 of our students that we award the degrees are online. So how does it look like? In a classroom, an instructor, a professor delivers a lecture to the students. Simultaneously, this lecture is captured by a few cameras, and also there's a streaming from the laptop with the whatever instructor presents, PowerPoint, PDF, or some specialized software. There's a streaming on web, and the students, online students, can simultaneously with on-campus students that are in a classroom, these online students simultaneously watch this lecture. After the lecture is delivered, this recording of the lecture goes to the server of the school, and students have access to this lecture until the end of the semester. This is actually a very powerful tool, in particular because students can go back to the lecture and review parts, especially of the material that presents difficulties. As a result, I would say 2/3 of the online students, or maybe 1/2, do not watch synchronously in real-time lectures, but only watch them later when it's convenient for them. Some students on campus also may skip a lecture because there's some other interesting things to do, like a date or basketball game or whatever it is, and they can watch these lectures later. Again, the quality is the same for the online and for on-campus students. And I also want to say that during the COVID pandemic, the distance education got boosted in all disciplines, not only in engineering. And the existing programs as ours that existed in distance education since 1970s actually was very well prepared to pandemic, because for us it was basically the same mode of operation, except that the students in the classroom disappeared. So in this emergency, the programs expanded, existing programs. All right, so now a little bit about more details about our program admission and the coursework. In order to get to programs, the Master of Science, one needs to have a Bachelor of Science degree in Science of Engineering. As I said, we don't require aerospace degrees. And the reason is that the space industry hires engineers of all flavors: mechanical, electrical, chemical, nuclear, you name it. Computer science also becoming very important in computer engineering. So these engineers work, for example, in a big company in Lockheed Martin or Boeing, working, for example, if you're an electrical engineer, maybe on the data processing unit or on the amplifiers or some electronics, and they becoming a very good professionals. They grow, but they cannot move to the top technical leadership positions in the space industry as a system engineer of a major subsystem on a satellite, or a payload, scientific payload, for example, or the entire mission. They cannot move there because they lack basic knowledge in orbital mechanics, propulsion, and others. So what I did at the very beginning of the program, I said, let's just concentrate on everybody who works in the space industry. Because if you try to get a Master of Science degree in aerospace engineering in other universities, you will have to go and just, they will require you to have Bachelor of Science in aerospace. And we said, no, we will take anybody, as long as a student has basic physics and mathematics required for engineering majors, regardless of the major, electrical, chemical, whatever. So this is one of the distinct features of our program, that we admit students without aerospace degree, bachelor's, but any bachelor in science and engineering. We require minimum cumulative grade point average GPA higher than 3. And in the past, we also required graduate record examination, GRE. Now, during the COVID, GREs nationwide were suspended. And I'm trying now just to bring it back for our program. And it's not clear because there's a resistance. Many students, potential students, don't want to take the exams. So this is a national issue or challenge in the United States, where to bring GREs back or not. It's also becoming a financial issue, because if you bring GREs, students would go to universities that don't require GREs. So again, it's a long story, but in my view, GREs are essential. It serves as a filter and helps to prepare students for graduate studies. And we also require 2 letters of recommendation. Now, the coursework requirements. So the students are coming with a Bachelor of Science degree, and we ask them to take 9 courses. Each course is 3 units. It means 3 hours of lecture time during the semester. And then students do homework. There's meetings with teaching assistants and all that. So 9 courses are required. This is more or less standard in the United States, 9, 10 courses for a degree. 4 courses are required the students should take. It's spacecraft system designs. It's basically an overview of fundamentals of space systems. Then a course on space environment and the interactions of the spacecraft with the space environment, spacecraft propulsion, rocket propulsion, and orbital mechanics. Then the students are asked to take 3 so-called core elective courses. These are the courses from the list of astronautics courses that we offer. They're all space focused. And then the students need to take 2 technical elective courses. They can take these courses from the list of our specialized astronautics courses, or basically any graduate course in any other department in the university, engineering or science department. It could be artificial intelligence, it could be design of integrated circuits, it could be vibrations in mechanical engineering, anything they want. We basically approve that, whatever helps a student reach educational objectives. Obviously, we don't allow courses to take in English and golfing and public policy or something like that. Only engineering and science courses. Master's thesis is optional, and very few students actually do them. And for online students, it's really not practical. But for on-campus students, amount of effort that would go to do research and write a thesis is much, much bigger than the effort needed to take the coursework with the equivalent number of units, credit units. It's easier to take courses. In addition, many students enroll in our program because of the selection of the courses. And this is the selection of courses in space systems that is unmatched in the United States. In a moment, you will see that. And also, many on-campus master students participate in student projects such as Liquid Propulsion Laboratory. In a moment, I'll talk about this as well. So now, students, just again, summary, I already mentioned most of these things. Of full-time students, half of our students are full-time, half of our students take courses through distance education network online. We have some students who are active duty military, as I mentioned, those officers, junior officers who decide not to continue, say, beyond when they're 35 years old or something like that. They want to go to back to the civilian life. Student background, that means they have Bachelor of Science degrees in all flavors of engineering, astronautical, mechanical, electrical, aerospace, chemical, nuclear, whatever. There are some students physics and astronomy, and we have also occasionally medical doctors, for example, coming to our program, maybe one medical doctor every 2 years. Typically, such a person thinks about becoming or applying to become an astronaut, and getting a degree in astronautical engineering obviously would help. I would say that 35% of students who are coming to our program, their background, Bachelor of Science, is aerospace and astronautical, 35% mechanical engineering, 10-15% physics, astronomy, mathematics, and the remaining 15-20% are all possible flavors of engineering: chemical, computer, electrical, nuclear, and others. So now this is the list of our current courses that we offer, and as I said, this is what built up our program and made it so big and so prominent in the country. And to my knowledge, no other university offers anything close to that, and practically all courses, with the few exceptions, are being taught by specialists from industry. I actually teach personally 2 courses. It's spacecraft system designs. It's an overview of fundamentals of space systems, and rocket and spacecraft propulsion course. And it's a little bit away from my space physics background, but again, I'm got involved in many programs, so it works very well. And I also actually offer short courses for government and industry in fundamentals of space systems as well. So, but anyway, these are the courses taught primarily by our part-time lecturers, and I color-coded them in different fields. On the top left, black color fonts, it's space systems courses, design of low-cost missions, space studio architecting, entry and landing systems, space environment. Then the blue color is the spacecraft dynamics, orbital mechanics, 1, 2, space navigation, space solar system navigation, spacecraft attitude dynamics, attitude control, then a cluster of propulsion courses: introductory rocket and spacecraft propulsion course, liquid rocket propulsion, solid rocket propulsion, advanced spacecraft propulsion, that's primarily electric propulsion, which is now very, very widely used on satellites, space launch vehicle designs, also physical gas dynamics, supporting chemical propulsion. There's courses on structures, dynamics, and strengths of materials, a cluster of courses on satellite subsystems, thermal control, power systems, systems for remote sensing, sensors, ground communications for satellite operation. This is actually a small class with the hands-on class where students using an antenna capture transmissions of satellites and working with that. Then there is a cluster in emerging space safety. So we have already 3 classes. I'm building this cluster, and I hope that one day we may, when we expand a little bit further, we will we'll make it a certificate, because space safety, reliability of space systems, safety of space operations, space safety is a rapidly growing area, particularly important today, and we must follow the trends in the industry and the space enterprise to be successful. And if you think about this, a very large number of commercial companies, new companies moved into the space area, trying to build rockets, satellites, applications, and many of them don't have these generations, going back to generations, experience in space, working with the government in 1970s, 80s, 90s, or even 2000s, working with the government where the space safety was strictly controlled and enforced by government agencies. So a lot of newcomers in the field, and space systems and rocketry remains inherently dangerous, as you obviously understand. So we need to space safety is rapidly growing in importance, and this is the important area for space education. And then we have another cluster of in human space flight. Interestingly, several years ago, a former astronaut joined our program as a teaching faculty, and he builds up this cluster of coursework in the human spaceflight, human factors in spacecraft operations, spacecraft life support. So because of his contribution, we were able to expand our program in this field. And there are also like PhD type courses, plasma dynamics, computational plasma dynamics, and others. And we're continuously developing and introducing new coursework to remain competitive and ahead of the pack. Now, a few words about student projects that I mentioned. We have two main programs. It's called Rocket Propulsion Laboratory and Liquid Propulsion Laboratory. Now, these student projects, they are not student groups that work on research driven by the faculty members. These are student groups that organized without faculty. They decide what they want to do, how they want to do. They make stupid errors, they learn on them, and they're getting very much excited about that. So if you bring faculty tied supervision, it will remove all the fun and these activities would disappear. Now, the faculty contribution remains ensuring safety, what's being done, because again, rocketry is a dangerous thing, and also helping with fundraising. Rocket Propulsion Laboratory primarily attracts our undergrad students, but also students from other departments. It's really across the other departments in the school, and even some students from the college are coming from the outside of the School of Engineering. It's primarily undergrads, but some master students there. They build solid propellant rockets and launched every year. They build a new rocket and launch it. They mix the solid propellants. They make the cases, composite cases of the rockets themselves, guidance, control, navigation, and everything. This group became prominent in 2019. They became the first student group in the world that shot the rocket above the Kármán line at 100 kilometers. The Kármán line, like viewed as a boundary of space. It's a little bit obviously nominal, but whatever it is. So it's a higher than 100 kilometers. And the last year in 2024, they reached the altitude of 140 kilometers. And these groups are very big. The students are really excited, spend many, many hours working there. 30, 40, 50 students in each laboratory engaged in the solid propellant rocket lab. And liquid propulsion laboratory is primarily master's students. Because if you think about the students that get exposed to the propulsion like liquid propulsion systems in the either senior year undergrads or in my class and the other classes on the liquid propulsion during the master's studies. This is a pretty sophisticated work that they are doing. They started with the gaseous oxygen and kerosene, and now they moved to the liquid oxygen, kerosene. So cryogenic engineering is very important, became. It's a regeneratively cooled engines. If you know a little bit about propulsion, you would immediately see how challenging is that technically. A lot of 3D printed parts these days. So it's a really sophisticated stuff, and the students present their results at the International Astronautical Congress, at the AIAA conferences. So it's a very, very good experience. And I also want to mention that if a student puts in a resume, graduating students, that he or she is worked at the rocket propulsion lab or liquid propulsion lab, it significantly increases the chances to get a good position in the industry, get hired, because as you would understand, that most of the projects in the industry, it's a team effort. And in regular classes, working on the homework, studying lectures, students don't work as a real teams. When you have a deliverable, something needs to be done, strict discipline should be enforced. And the rocket propulsion lab and liquid propulsion lab, they offer this opportunity for students to learn how to work in the team. And some of them emerge as the natural leaders, technical or managerial, in these teams. So this helps dramatically for them to get very good positions in the industry. So finally, I want just to say a few words about some common questions, because it may preempt some questions that you may have. Typical time to complete the program for full-time students, it's usually 3 semesters, 1.5 years. Typical load is 3 courses per semester. Plus all these laboratories they're working and doing other things. Part-time students take usually 1 course per semester, so it takes 3-4 years, maybe 5 years to get a degree. Course sequence, we don't require the required courses before electives. It's really up to students, but most students start with the required courses. There are a few exceptions. For example, if you want to take orbital mechanics 2, you have to take orbital mechanics 1. Waiver of the required courses. What is this? You are coming from a different universities where you get a Bachelor of Science degree, and you already had in the senior year spacecraft propulsion course. There's no need to repeat our course. We will waive this requirement, and instead student will take an additional technical elective course. Obviously, distant students, when they occasionally come to Los Angeles, for example, on a business trip, they are coming to live lectures to introduce themselves, to meet professors in person. It just happens all the time. Now, one thing that is very important is industry interest. Enrollment dynamics in the online program is very important to validate the quality of any program. And the reason is, if you're an engineer hired by Boeing or Lockheed Martin, you can go and get Master of Science degree part-time online at any university in the country. Boeing has, I think, 80 approved engineering schools. That means that these students from industry, if they come to your program, this is a clear indication, because they could have gone to other universities. So this becomes a clear indication that your program offers something of their real value. So it's not marketing or sales speech, because again, there are some great salesmen that can sell you something that is not proper quality, but this is a real proof. If the online program is doing well in this highly competitive environment, that means that the quality of the entire program is very good. And a little bit more about this picture in the United States. So each university with the aerospace department, again, statistics only for the aerospace program, to combine aeronautics and aerospace, astronautics together. So each university produces so many master students. If you look at the figure on the left top, it shows the distribution of the number of universities in the United States that produce so many students. For example, if you look at this figure on the top left, 2 universities awarded on that year, 2016-17, between 110 and 120 students. Then the two universities awarded degrees between 70 and 80 degrees, and between 20 and 30 degrees, 12 universities awarded. And the red box shows where our program at UEC, Master of Science in Astronautical Engineering, was there. At the bottom is the latest year for which I had statistics. 2021, 2022, we became number 4 in the country, again with the very few faculty members and relying on the part-time lecturers primarily. We became number 4. We are producing more than 80 masters per year, only 3 universities ahead of us. And finally, lessons learned. This is the last slide. On the right, there is a figure that I compiled, the worldwide space enterprise in billions of dollars, US dollars. And it's a little bit, numbers are not sort of a very strict because the methodology, how the Space Foundation produces these numbers, it evolves with the time. Also, some countries are not transparent, like the People's Republic of China or the Russian Federation. It's not transparent how much is being spent on space. There's a currency calculations and all that, but it's general trend. The blue at the bottom is the government spending that was below $100 billion per year. Now it's slightly above $100 billion per year. It's both military and civilian, like NASA in the United States, and this blue is dominated by the United States, like 75% is by the United States, 65%, 70%. It's United States. Commercial space, it's orange on the top, is growing. About in the late 1990s, or maybe at the year 2000, commercial space overtook the government space in terms of dollars, and these expenditures continue to grow 6-7% per year. Today, it's more than $1/2 trillion. Space enterprise worldwide continues to grow. More and more countries getting there. Huge constellations being deployed of the satellites. More stuff is being done from space. Also for national security, more and more countries are getting interested. So space is growing, and space education space engineering education should follow or support this growth. Keep in mind that a lot of people who will work in this space building satellites, applications, they're really not in the really space areas. It may be electrical engineering, computer science, and all that, but the core expertise that keeps everything together, glues everything together, still orbital mechanics, propulsion, attitude control, attitude dynamics, spacecraft power systems, space communications, and others. This require astronautical engineering, and this is the area where we are. So the lessons learned. The pure space engineering academic department can and will be successful and complement traditional aerospace programs. Unfortunately, other universities didn't follow our call and didn't form independent departments in astronautical engineering. There are a lot of internal politics, university politics in that, academia. Again, this is a story for a different presentation, but we are, again, very, very successful nationally and internationally, the pure space engineering department. So what is necessary for success? What are the lessons? First of all, availability of practicing leading specialists in the highly specialized areas. It's very important. But this is not enough. You still need to have a dedicated, knowledgeable, and I would say charismatic core tenured faculty. Somebody needs to lead it on campus. Online component is very important for validating quality and relevance of the program to the real needs of the space enterprise. I already talked about this, because the engineer working at Lockheed Martin or JPL can go to any universities and take classes online. If they come to your program, that means you provide something of value. It's a validation. Program identity and clear identification of the customer. So what it is very important from the very beginning to identify what type of students or working engineers you want to target by your program. For example, in our case, we are not from the day one, I always stated, we are not a systems engineering program, and we are not a space studies program. Now, space studies is, there's a few universities worldwide that attract actually a lot of students. It's a light on engineering, light on math, light on science, but they have additional courses in space law, space entrepreneurship, space public policy. So for the graduates from these programs, the best places to work is the think tanks rather than industry doing and making products. So we are clearly focused, not system engineering, not space studies, but hardcore engineering for students who would go and fill cubicles in companies and will be building new systems. Packaging of the coursework is also important. So what is this? Very often students are coming to a program and they have very vague idea what they want to, which courses they want to take. And we have 3 times more courses than the students can take. So which one should be chosen? And we tell them, hey, if you want to specialize in rocket engines propulsion, these are 8 courses and just choose 3, 4, 5 out of these 8. If you're interested in spacecraft dynamics, these are another half a dozen courses. Just choose your technical electives from these courses, and so on and so forth. Also, it is very important to understand and pay attention to industrial trends and listen to the feedback for the full-time working students in industry. This is something that not easy to do in academia on campuses, because very few people that I know on campus, professors, would tell you that they want to hear opinions of somebody else. They think that they know almost everything, but it's very important to understand the industry where your graduates will work and adjust the program to meet the real needs. And finally, internal to the university lessons, financial soundness. What do I mean by that? If a program in a university is a financial burden for the school, it will be very difficult to innovate, to expand, because again, you require money from the dean, the provost, and others. But if you financially sound, if you bring profit to the school, then it's much easier to get the permission to experiment, to expand the program, bring classes. So it's a very important. This again, also an argument of financial soundness is something that many faculty members really don't understand and don't like, because again, the intellectual value is considered so important and all these financial things are irrelevant. So in the real world, it's not the case. If you want to have a program successful in a university, it must be financial sound. And another, administrative independence is very important to insulate the program and insulate particularly part-time lecturers from internal university politics. To do that, usually a program needs a strong, charismatic leader who can speak forcefully and act forcefully on campus. And it does not bring friends, but it allows the program prosper. And on this note, I want to finish. Thank you very much for your attention. I will send the slides, PDF of the slides, to Betty. So if anybody would need them, please feel free to take it from her. Thank you. Shashe.
Thank you, Mike. Thank you so much for this detailed description of your program. And obviously, obviously it's very rich program, and then you well deserve the praise from other people, from your colleagues. The I wonder whether we have a question from the participants first. I would just ask them if you have questions. Some of you have questions. You ask any kind of questions, like if you want to go to USC or you're interested in some particular area. You could, now is the time to ask Professor Gruntman. So you just raise your hand or just turn on your microphone and speak. Yeah, please, Dalton.
So, hi, Professor Gruntman. My name is Dalton, and currently I am a undergraduate mechanical engineering student with a focus on propulsion, and I'm planning to pursue a master's degree in the U.S. So, ideally, leading to a job after graduation. But however, I've noticed that many space-related career paths have citizenship restrictions. And so my question for you is, based on your experience guiding students in astronautics, what kinds of career paths have you seen international students pursue in this field?
This is a very good question, very important. I would suggest that you pull out this PDF that I listed in this talk, and because I discuss in a couple of articles, there's a half a page here and half a page there of the effect of export control that governs that, and the ITAR regulations and others. When students ask me this question, first of all, I want to tell you that in the astronautical engineering in general, we have foreign students. Actually, in our program, in the master's program, we had students from, I think, 15 or 18 countries during these 20 years. But the number of fraction of foreign students is significantly smaller than in, say, electrical engineering or computer science or industrial systems, where there are no such restrictions. I usually say that for a student pursuing a degree in space, you are not the first one and you are not the last one in this difficult situation, finding how to proceed. It will be more difficult, no question about that, compared to those with the green cards. So your green card is needed to proceed. Really, it's citizenship is better, of course, but the green card is sufficient for many jobs. So it will be more difficult, no question. Some students find some fellowship, for example, even in the government, like JPL had fellowships for foreign students to continue after the graduation. There are also some students take jobs in the companies that are not in space for a couple of years before they will get green cards, and then they move back to space. Some finding, so it's necessary to knock at many doors. It will be more difficult, certainly, but again, you are not the first one and you are not the last one who are in such a situation. And also the situation in the United States is very fluid now. Overnight, there may be suddenly a green light for STEM, science, technology, engineering, mathematics, for STEM. They suddenly could change and become much more favorable. But again, it's unpredictable completely, but we are now during this period where changes may happen. And if they happen, it will be overnight.
Okay, but I am curious, Dalton, where are you studying now? You say you're undergraduate, you're interested in propulsion, and where are you studying?
Oh, I'm currently a student at National Yangming University.
Oh, okay, I see. I understand. Yeah, right. Yeah, I mean, it's not easy, right? I mean, because you're in this particular area.
Yeah.
And but try, and
yeah, and as I said, we had students from 15 or 18 countries, a number of students from India. In the past, there were some students, a few, but still there were students from the mainland China, but then now they disappeared completely. Again, it's a geopolitical environment. It's
Now, I remember, I know that there's a student from Chengkong University, who is now studying at USC and got himself involved in the rocket lab. I will take out his name and give it to Dalton. But if you could write down your email address, I could send the information I know to you. Okay.
Okay,
all right.
thank you, and thank you for Professor Gruntman's thorough explanation.
Yeah, but try to read, just pull out this. It's like 60 pages, but just do Control F and you will find ITAR or foreign, and you will find a couple pages discussing in details.
All right. Other questions from the participants, from the audience? Just raise your hand or turn on your microphone. If not, let me ask the last question, which is, why don't you like teaching system engineering?
So it's not that I don't like it. It's not where the most of the jobs are. So a good system engineer should at first, to succeed in becoming a specialist in one area or maybe even in two different areas. After that, if an engineer can move towards systems engineering, and this would be highly rewarding because it will be on the high level. Those engineers who go immediately after Bachelor of Science degrees into the systems engineering, they end up, because they don't have experience, they have never done in the specific domain anything, they will end up following the paperwork. It's called flow down of requirements, purely pushing papers, and they can be fired any moment and the company will not notice that. So the best way to go to system engineering at first to excelling in one or two areas. What happens, we have in our program actually students who already have master's degrees, primarily in the electrical engineering. They work very successfully in the space enterprise, and in order to become systems engineer, they are lacking pure space expertise. So they come to our program to get the second master's degree, and then they are sort of prepared. You can learn systems engineering not by coursework, but simply by doing things. It's a lot of common sense involved. And so from that, but having courses focused on systems engineering will not help students find jobs, let me put it this way, or get promoted. There are some programs in the industrial systems, usually departments in the departments of industrial system engineering, who focus on systems engineering in general, not in space, but in general. And we had to choose, and the choice that we made was actually correct, as our numbers show. We're successful, we grew, we attracted students. And we have a couple courses with some elements of systems engineering. For example, we have a course by Jim Wirtz, who has become behind these SMAD textbooks, who teaches design of a low-cost space missions. It's a really systems engineering course, how to twist everything to reduce the cost, but it's not the focus of the program. Program focuses on the particular areas where the engineers can be promoted if they work already or get hired to jobs.
Well, so thanks for the explanation. I think that sounds very reasonable to me. I mean, that's why I believe in that too. Only that our education system now, we have in Taiwan we have 4 master degree program in system engineering.
So Master of Science degree in systems engineering is not that bad, because there's a few programs that I heard about. They have Bachelor of Science degrees in systems engineering, which complete nonsense to me. But again, I'm not CEO of Boeing or Lockheed Martin.
Complete nonsense. Okay, it's a very strong word, Okay. Any other questions from the audience? I think that we have more or less exhausted, exhausted my wisdom at this point in time. And thank you so very much. You know, I can see that you're still very energetic and dynamic. And I wonder whether you will build up another program. Okay. Okay, good. And I hope to see you. You know, last time I was in San Diego and we talked, and but I said that once you have chance to come by, you know, Taiwan, just come over, right? Let's know.
Certainly, I will do.
Yeah.
It will be a pleasure.
Yeah, great. So thank you so much for everybody for coming to this online seminar. And if you are interested in mice, you know, that you miss something, you could always go back to the recording. We will put on it in no time. And thank you, Mike.
Thank you.
Yeah, bye-bye.
Bye-bye.